Hey guys, how's it going? In this video, I'm going to go through this leak code number 818 race car. And this question was asked by Google for 90 times for the past 6 months, Amazon for 14 times. So this is quite popular. Let's dive in. Your car starts at position 0 at speed +1 and on an infinite number of lines. Your car can go into negative positions and your car drives automatically according to the sequence of instruction accelerate and reverse. So when you get an instruction of A, your car does the following, the position will add to the speed and the speed will multiply by 2 for the next one. Okay. And when we get an instruction of R, which is reverse, and it will do the following, the speed, if the speed is positive, the speed will become -1. Otherwise, the speed will be +1 and no change in the position. So for example, if we have a command of AAR, the car will go to position of, so it starts from 0, it will go to 1, 3, and 3, and then the speed will go as following, 1 and 2 and 4 and -1. And we are given a target position target, we need to return the length of the shortest sequence of instruction to get to that the target position. So let's go through this command to see what's going on in here and why it goes from 0, 1, and 3 and 3. Okay, so we have an instruction of AAR at time 0. The position is gonna be 0 and the speed is gonna be +1, and this is given in here, right? And this is our starting point, and then at time 1, the position will be increased by 1. Okay, because the position we begin with is 0, and then we +1, right? And then we end up with a +1 at the position at time 1, and then the speed will be doubled, right? So this speed will be used for the next time step, which is over here, the T2, right? So T2 is going to be +1 plus the 2, right? And this is the speed of the previous time step, right? So the position is going to be +3, and then the speed will be again doubled, so it will be +4, okay? And then at time 3, and because the instruction is to be a reverse, right? So the position is not going to be changed, right? This is right here. And then the speed will be reversed to be -1, which will go the other direction, okay? And let's look at some example here. So we are given a target of 3. The output needs to be 2. And the reason why is we had just simply issue 2 instructions, just keep accelerating like A and A, right? So the position will go from 0 to 1 to 3. And if our target is 6, right? So the shortest instruction is gonna be A, and then reverse, right? And then A. And why we need to reverse? Because we overkill, right? So we go from 0, 1, 3, and then jump to 7 because the speed was 4 at this point in time. And actually, here we are overkilling it because the target is 6, but we are at 7, so we need to do a reverse, right? And then the position is not going to be changed, so we stay in 7, but the speed going to be -1, and then we will accelerate again, which would change the direction to be -1, right? So the direction will be to the negative side, right? So you go from 7 to back to 6, and this is the second example, and we have also some constraint over here. And actually, there are 2 ways to solve this problem. One is using the dynamic programming, and the other method is use the Dijkstra method, which is use a priority queue, which is a BFS approach to solve this problem, which I'm going to talk to you about this solution. I think this is more intuitive. Let's dive into the solution together. As I mentioned, this is going to be a priority queue. I'm going to use a heap to perform all the the queue operations, right? So I started with just a simple queue over here, and I do a heap queue dot heapify. So and then at this point, this one will be a heap, and I heap push the starting point. And as you can see over here, the convention I'm following over here is the first element is the number of steps that we have traversed so far. So at the starting point, we haven't gone anywhere. That's why the end steps is gonna be 0, because again, this is our starting point. And also we have the current position, and the starting point, we started at position 0. That's why it's just gonna be a 0. And the speed that we are beginning with is going to be a positive 1, right? So this is all these the starting conditions over here. And once again, so this is just the starting position. And while the queue is not empty, right? And then we pop it off by using this heap queue dot heap pop operation. And what's going to come out is the number of steps that we have traversed so far, and the current position, right? And also the current speed, right? So this is the node that I have already put it in here, right? And then we have a exact condition where if the current position is exactly equal to the target, in that case we are done. And we need to return the number of steps that we have traversed so far, and then we exit from the function. And then the projected next position is gonna be the current position plus the current speed that got popped out from the queue, right? So the next position is gonna be the current position plus the speed, and then the next speed is gonna be doubled of the current speed. And if we are gonna issue the accelerate instruction, right? So we're gonna push this node to the queue essentially, right? So this is the next node that come from the current node, right? So the time step, the number of steps gonna be added by 1, right? Because we are basically adding 1 step from the current and then go to the next. And this actually the cause for our priority queue, right? So when we pop off a node from the queue, it will always pop off the one that has the lowest end steps, right? That's why we need a queue. And then it will go from the current position to the next position, and then the speed will be doubled as well, right? So this is the case where we are issuing the accelerate instruction. On the other hand, we might issue a reverse instruction. And what's the condition of that? It's gonna be if the projected next position is greater than the target, so we are overshooting it, and also the speed is still accelerating. In that case, we will keep going the overkilling direction. And on the flip side, if the next position is smaller than the target, so we are still need to move forward toward the target. However, the speed is on the opposite direction. In that case, we also need to issue a R instruction, right? How do we do it? Just whenever we issue a R instruction, the position is not going to be changed. That's why we will stay where we are. However, the number of steps will increase by 1. and then the speed will change in direction. And some people are confused about this condition. I think I found a very good blog post in here, discussion board, and this person, David E. something, I think he has a very good illustration. So um, these two conditions over here that we looked at together, it adds the possibility where you can reverse and then reverse again in a consecutive steps, if that makes sense. So he's giving an example. So let's say that we are currently at position 3 and we are at the speed of 4. So obviously the next step is going to be overkilling it, right? Because we are trying to get the position 5, but the current speed is 4, right? So if we keep going to that direction, the next position is going to be 7. So we are overkilling it. So that will fall under this condition over here. So the next position is going to be overkilling the target. However, the next speed is still positive. Okay, so in that case, we can simply issue a reverse instruction. And after we add a reverse instruction, right, we need to issue another reverse instruction to go back to the correct direction. Let's continue the example, right? So we first reverse and then we will stay at position 3. However, the speed will change to be -1. And then, so at this step, actually it falls under this condition, the other one, right? So the next speed is smaller than 0 because the next speed is gonna be -1 over here. However, the next position is smaller than the target, right? Because the position is going to be 3, but the target is 5, right? And therefore, again, that falls under this condition. And then we need to reverse it again, right? And then the speed will be back to 1. And then we move forward to position 4. And then you can read the rest. It's very similar idea. So this guy catches this case in here. And that's it. So the code is not very complicated, but the thinking it takes a bit of time. So for time complexity, this is interesting because for a normal BFS approach, the time complexity typically is big over n. But in this case, because we are doubling the speed every time, so the time complexity is going to be big over log t. And to be precise, it's going to be log base of t, a log base of 2 to t. So essentially, the time complexity I'm going to write over here is going to be log base of 2 of t. So this is the number of iteration that under this while loop. And for each of the operation for this heap hop, it also takes big log 2 of t as well. Because again, this is a binary heap, right? And also this heap pushes as well. So it's going to be log 2 of t times log 2 of t. And it depending on how many heap push, so it's going to be another log 2 of t as well. So that is the time complexity, and the space complexity is going to be over the log 2 of t. Just, we don't need to multiply anything. And yeah, so this is my solution to this problem. I hope you find this is helpful. Thank you so much for watching. See you next time. Oh, before I let you go, I'm going to run the code in front of you to make sure to prove to you that this actually works. Right here. Thanks again.